Got a question, guys? Question, guys?
So, as I'm reading EAS, what I noted is that HNO3 is often used with sulfuric acid. Sulfuric acid is a stronger acid than HNO3. But we use acetic acid, and that's a weaker acid in the lab.
Yes. Yes.
Is the reaction the same? It shouldn't be, should it?
Sulfuric acid, as we'll see, is commonly used for nitration. It's actually a catalyst. We'll state why. But not all aromatics need the catalyst. Some will react without, and fluorine will react without. If it's an activated aromatic, it'll react without. Acetic acid, probably not strong enough to be a catalyst. It's mainly a solvent in the reaction. Once we get to EAS, you can ask again or think about it again.
Okay.
In the workbook, it does state when that's introduced, sulfuric will not be used and is not needed. But yeah, traditionally it is used. If we had used sulfuric acid, the nitration would have been very exothermic, much harder to control, probably would have likely turned orange, deep orange. So we didn't want it to proceed that fast. Question?
Do you have an extra purple sheet?
You need a purple sheet? Okay guys, let's get started. Hope you have a good week. Let's get it going. Yeah? Got lots to cover. So we've got a yellow and a white. See where we left off at. Document camera. Any questions about aromatics up to this point? We were looking at ions. I believe we finished up why this one's aromatic, this one's easy to form, that one's not. Thus, this is fairly acidic for a hydrocarbon because it's going to a real stable anion, much more stable than you would expect for a hydrocarbon. The pKa about 16 shown below. I believe we left off right here. This guy here, non-aromatic. There's no p orbital here. It's sp3. No p orbital. It's not a fully cyclic conjugated system, and so it is game over. Non-aromatic. Neither anti or aromatic. What if we remove an H and two electrons? So essentially we have to remove H minus to get this. Kind of very difficult and odd to do, but theoretically that's how you get this. We'll see other ways to make carbocations. You know plenty of ways to make carbocations. We can also have the 5-membered ring for comparison here. Let's look at this guy here. By the way, I want to do an MO diagram for one of these before we move on. But we didn't do one for that. Is this a cyclic conjugated system?
Yes.
Yeah. Hybridization of a carbocation typically. sp2. That means it's trigonoplanar. There's an H here, yeah? There's 2 there, there's 1 here. You can draw in the H, trigonoplanar. What's left over? P orbital. What's in the P orbital? Empty. Well, all the others have P orbitals. One electron makes pi bond. I'll try to draw these so they look like they're overlapping. One electron makes pi bond. One electron makes pi bond. What do we have here? Fully cyclic conjugated system of p orbitals. How many p orbitals in the system? 7 p orbs. How many electrons? 6 pi electrons. Okay. Cyclic conjugated, yes. How many pi electrons? 6. Oh, what does that sound like? Sound like a 4 plus 2 number. Cyclic conjugated system, 6 pi electron. Aromatic. Okay, this is an aromatic cation, yeah? That means it's going to be much more stable than your regular old cation. So it's got this magical cyclic conjugated system of electrons. Anions can be aromatic, cations can be aromatic. What about this guy over here? Aromatic or anti or what? Is it a cyclic conjugated system?
Yeah.
Somebody said no. P orbital here?
Yeah.
Okay. P orbitals all the way around. We have 5 p orbitals. How many pi electrons? 4 pi electrons. Okay, if it's cyclic conjugated, what is it? Is there any reason or way it could be non-aromatic? It wasn't planar. Do you think it? Typically, a carbocation is going to be sp2. I'm not 100% sure, but I believe this is anti-aromatic. Here's what I'm definitely sure of. It's definitely not what? It's definitely not aromatic. Again, things are often not anti-aromatic because they avoid it somehow, but typically carbocations have to be sp2. So assuming planar, we say it's anti-aromatic. That carbocation is very difficult to form. You can see some applications of this. How do we typically form carbocations? Where do we see that? Well, in reaction mechanisms. For example, we may say, hey, if we got this alcohol, looks a little odd with this ring here, but it's all right. HBr, we try to do a substitution reaction. What do we want to do? Protonate the OH? And maybe it ionizes. If it ionizes, what does it give? You can protonate and then ionize. Give this. What is this?
Secondary resin stabilized.
Yeah, but it's much more than that. It's also known as. We just did it. Aromatic. It's an aromatic intermediate. I'm doing SN1 here. Okay? These are probably SN1 reactions. What's the rate determining step? Formation of carbocation. Is this going to be easy to form?
Yeah.
Yeah. Be easy to form. That reaction there shown should be very easy and fast. On the other hand, the reaction on the right is going to be very difficult. Because over there, the carbocation is going to be what? It'll be the 5-member carbocation, the one we just did right here. Is an anti-aromatic carbocation going to be easy to form? No, it's probably not going to do it. Definitely not going to be easy. So here's an example of aromaticity affecting reaction rates, because we understand that an intermediate can be anti-aromatic or aromatic. And so we're adding to our knowledge of reactions, mechanisms, predicting kind of rates. Does that kind of make sense about these intermediates?
If it's difficult to form the carbocation, is it just going to try to go SN2 instead, if it can?
That's a good point. If it could, yeah. You might protonate and then do Br minus. And so you, in terms of proposing a mechanism, you may propose SN2 and say, hey, I want to avoid SN1 because of this reason. I don't know if the reaction on the right is actually known or not. But what I do know is it's probably not SN1, and definitely if it was, it's not going to be as fast as this guy over here, this reaction over here. So we saw aromaticity influence acidity, and now we see aromaticity influence reaction rates based on intermediates. Okay. Let's move to heterocyclic compound. Hetero meaning non-carbon, different from carbon. Cyclic meaning cyclic. Typically, heteroatoms are nitrogen, oxygen, sulfur are the most common. Many others, though. We'll also see group 3 heteroatoms, such as boron, aluminum. Pyridine. We've seen pyridine before. We've used it as a base, for example, when we did tosylates, made tosylates. It's like a benzene, but it's got a nitrogen instead of a CH. Nitrogen's got a lone pair. Is it aromatic or anti-aromatic, or none? First off, is it a cyclic conjugated system?
Yes.
What's the hybridization of the nitrogen? What type of orbital is the lone pair in?
No, it's in an sp2 orbital.
Not in a p orbital. LP and sp2. If you graph it like we did at organic 1, it is sp2, and so it's got 3 hybrids, p orbital left over. What type of bonds do you see the nitrogen making? Sigma bond to carbon, sigma bond to carbon, and pi bond to carbon. All together now, that's your double bond to carbon. Here's a single bond to carbon. What's left over? Lone pair left over. There you go. Lone pair is in a hybrid sp2. The nitrogen does have a p orbital, right? Okay. Now it's already drawn here. I took this from the web or somewhere. Here's the nitrogen over here. Okay. Trigonal planar. Boom, boom, boom. There are your hybrids. What's left over? P orbital. How many electrons in the nitrogen p orbital?
2.
One.
Oh,
1, because here, if you do it right here, one electron makes pi bond. That's the pi bond you see there. The lone pair is in the hybrid. The lone pair is out here in this hybrid that's perpendicular to the pi system. Well, every other p orbital has 1 because there's pi bond, pi bond. Basically, you got two carbon-carbon pi bonds and then a carbon-nitrogen pi bond. Of course, we know that it's all continuous overlap, so how many p orbitals? 6. How many pi electrons in the system? 6. What do we got? Aromatic. But importantly, the lone pair is not in the pi system. The lone pair is in the hybrid. Because the lone pair is not in the pi system, the lone pair is basic. If the lone pair is in the pi system, it would be delocalized. Either by a resonance argument, but now we have a molecular orbital argument. And those electrons, if they were in the pi system, would be spread out all over the molecule. They're not. They're in a hybrid. Thus, these lone pairs are basic. Pyridine is a base. Now, it's a weak base because it is an sp2 hybrid as opposed to an sp3 hybrid. So it is, what, 33% S. And so it's held close to the nucleus a bit relative to sp3, but it is still basic enough to be a mild base. So this is the structure, the p orbital description, the p orbital diagram or illustration, etc. So that's called a pyridine type nitrogen. We've been laying the foundation for that since the first week of Organic 1, right? When we graph things and understand structure, hybridization. There's not a whole lot new there other than just saying it's aromatic. Another type of nitrogen that's common in heterocycles is your Parole type nitrogens. I don't think we've ever seen Parole, but it's a 5-member ring. Nitrogen, of course, it has a lone pair. The drug Lipitor has a Parole ring. What's the hybridization of this nitrogen?
sp2.
Yes, sp2. And the lone pair is in what type of orbital? P orbital, good. And if you graph this, you would have sp2 and a P left over. What type of bonds do you see? Sigma to carbon, and sigma to H. Lone pair is in the P orbital. Now this is just turned sideways, but we have 2 p orbitals pi bond, 2 p orbitals pi bond. That's that. Here's your p orbital of the nitrogen. It has a lone pair. See, the hybrid only has 1 electron. Well, there's 3 hybrids. But the one that's coming out here perpendicular to the pi system is interacting with an H electron. Of course, the H orbital is a 1s orbital, and that's overlapping to make a sigma bond to hydrogen. P orbital has 2. Now we have cyclic conjugated system. How many pi electrons? 6 pi electrons. And thus we have aromatic. Parole is aromatic. But here, the lone pair of the nitrogen contributes to the aromaticity. It's in the pi system. Jordan.
These like odd number of like pi orbital or p orbitals, can you do like an MO diagram or no? Since like
Yeah, and I forgot we didn't do one before we left the O's. I want to go back and do an MO of like one of the hydrocarbon ions.
Does the MOs work the same for, Parole?
4 plus 2. So,
No, does the, MO, the diagram work the same?
with heteroatoms, it becomes a little bit odd. Because these guys are not as delocalized as benzene. Benzene is your perfect delocalized system. See, these guys, because the nitrogen is inherently more electronegative than carbon, it's not as fully delocalized. Nitrogen sort of holds on to some of the electron density. Let's go back and do an MO previous page. So this is a Parole type nitrogen. Is Parole nitrogen basic?
no.
No. Typically electrons that are in p orbitals we say are non-basic. Now there's like one exception to that. Parole is no exception. Parole is pretty much non-basic in terms of a classical base. But pyridine is basic. It's a difference of where the lone pair is. Okay, you can have plenty of other heterocycles. Many of them have common names, and there's plenty that have just systematic IUPAC names. Imidazole, that's where we add another nitrogen to Parole, called imidazole. There's 2 nitrogens. Which nitrogen is basic, the top or bottom? Good. You've got to understand where these lone pairs are at, etc. This is a Parole type nitrogen, the lone pairs in the pi system. Okay, it is aromatic. It's 6 pi electrons. Or is it 8 pi electrons?
6.
What about, there's 2 more.
They're not in it.
Yeah, but they're not in the pi system. Okay? You got to understand basic hybridization structure. 6 pi electrons. This nitrogen here is considered basic. Histidine is an amino acid that contains an imidazole ring. Histidine is a basic amino acid. That's because the side chain is basic. It's that nitrogen there, not that one, but that one. Not that one. Y'all learned amino acids in some classes?
Yeah.
Some of them are basic, some of them are acidic, some of them are neutral. Histidine is a basic amino acid.
Why is it PKA 6?
Where does it say that?
We had it on biology.
Okay, what does the pKa refer to?
This,
You're calling it a base, so the pKa refers to the, yeah, pKa refers to that. And that's a pretty good acid. I mean, why? Because imidazole is not of that non-strong base. It's a fairly weak base. That has a pKa of about 6. I would have said 7. So that looks like a, pyridine is 5. pKa of pyridine is 5. Since this is quoted as 6, is this more basic or less basic than pyridine?
More basic.
Yeah, it's a little bit more basic than pyridine. Why? Because you can draw a resonance structure of the cation. These electrons can move here, these can move up, and you can get a resonance structure of your cation. That means it's more stabilized than not. That extra stabilization of the cation makes it more willing to form. If it's more willing to form, that means the original is a little bit more basic. Imidazole is seen in drugs. Anybody ever heard of Versed? Drug given sort of to, if you have like an outpatient procedure or something, they want to put you kind of almost out, give you a little shot of Versed. You'll be happy for about 2 or 3 hours. Okay. It's got an imidazole ring up here. It's fused to a larger heterocyclic ring. It's got 3 nitrogens. Of the 3, which one is not basic?
Middle.
One in the middle is not. The other 2 are basic. One in the middle is a Parole type nitrogen. The other 2 are pyridine type nitrogen. Okay, don't let me forget to do the MO back on the other page. You can have other heterocycles. Furan. Aromatic, anti-aromatic, or what? How many pi electrons? But I see 8 there. What's the hybridization of the oxygen? sp2. Coming out of Gen Chem, you would have said sp3, because it has 4 regions, but we know that if a lone pair is next to a p orbital, etc. If we graph this, what do we end up with? This oxygen here has sigma bond to carbon, and what else does it have? 2 lone pairs. 1 lone pair is in a hybrid, 1 lone pair is in a p. Only 1 of the lone pairs is in the p orbital. If we do a p orbital diagram of this, three lines are trigonoplanar. There's your 3 hybrid orbitals. Sigma bond to carbon, what's this orbital here? That's 2, that's a lone pair. I mean, you can make that an orbital if you want. A lone pair coming out there. The other lone pair is in the p orbital, but you also have p orbitals over here. Pi bond there, pi bond there. But of course, we know it's not just 2 pi bonds of a lone pair. We know it's fully conjugated. This leads to MO, where the electrons are spread out all over in molecular orbitals. Fully cyclic conjugated system with 6 pi electrons, aromatic. This is furan. If you add 2 H's here and 2 H's here, what do we get? Basically, if we add 4 H's, what do we get? Tetrahydrofuran, which is just plain cyclic ether. THF is a common solvent. Furan you don't use as a solvent because the p orbitals, the pi bonds make it sort of reactive with pi bond chemistry.
shouldn't it be stable though?
Can we what?
So shouldn't it be stable though because it's aromatic? Or is it because of the other lone pair?
It is aromatic, it is stable, but heterocycles are not quite as stable as benzene. They're still stable. The reason is, really have to start drawing like traditional resonance structures. We draw a traditional resonance structure, maybe like these electrons here and these electrons out. Does that look right? One lone pair left. What's the charge of the oxygen? Positive. Okay? See, the problem is oxygen doesn't like becoming positive. And so it doesn't like to share its electrons. And so these electrons are not fully delocalized. And we get into very gray area here. Well, is it delocalized? Is it not? Furan, see, benzene is the granddaddy of all aromatics. It is fully delocalized evenly. And that's why we often just see it drawn like that. I mean, you can move electrons here, electrons there, electrons here. And it's like, well, it doesn't matter. It's all just equally spread out. But here, you never see heterocycles drawn like that. Especially if you know chemistry.
Not even purity?
Pyridine is more so because, yeah. But these guys know because this means the electrons are just equally spread out here, and that just goes against your intuition. Would you expect the electrons to be equally spread onto carbon when you have an oxygen? No. No. So there is some degree of localization. So here's a good thing. How would we judge the aromaticity? In this class, we will either say it's aromatic or not. But in real life, there's actually degrees of aromaticity. How aromatic is furan? Which is more aromatic, furan or thiophene? We're not going to ask those questions. We'll see what, we'll ask it in a minute, but we're really not going to go there. It's called the oxygen. It's kind of a greedy little guy. Doesn't like to be fully delocalized. Let me introduce thiophene and then I'll say some more about it. Thiophene, sulfur being just below oxygen in the periodic table. Very similar bonding. And so it's the same thing we discussed over here. What's the difference between your oxygen and sulfur? There's electronegativity. So, which one is more willing to let these electrons be fully delocalized? Sulfur. So, which one is more aromatic? From that argument, thiophene. Is that why you said thiophene, Kingsley? Oh, yeah? Okay. Yeah. Because sulfur doesn't mind saying, hey, let's equally share these electrons. Kumbaya. Okay? Oxygen's like, hold on now, I want to keep my electrons. I don't want to participate in this fully delocalized game of aromaticity. But, hold on. What's the difference if we drew our orbital description? I already drew this. What's the difference if we... What's the difference if we draw thiophene? Running out of time.
What's the second?
What's the difference?
Bigger?
Bigger? Bigger what?
Bigger P orbital.
Bigger p orbital. Okay, I don't have enough room. Sulfur is bigger atom, we're down, okay, as you get larger orbitals. What would the bigger p orbital, what kind of consequence would that have for the bonding?
More delocalized?
No, I think it'd be less likely to interact with the others, wouldn't it? Because it's so much bigger.
Yes, it's actually less likely. You don't have as good an overlap. So you got sort of you got sulfur, which is more inherently more eager to overlap or willing to overlap, but you got a bigger orbital which can't overlap as well. So which is more aromatic?
It's hard to say.
Might need some experimental evidence. Don't forget about your orbital size, okay? And we never really mentioned that when we talk about resonance. The size of the p orbital can affect overlap. And we'll probably mention that when we get to reactions of aromatics. Thiophene is known to be more aromatic. For example, furan will react as a diene. I mean, furan will do Diels-Alder reactions. Furan, if you're also reacting with bromine, it'll do addition reactions. That's reactions of just dienes. Where thiophene typically will do substitution, thiophene it's harder to do Diels-Alder because it's really not a diene. It's more of a delocalized. Okay. What about Parole? How many lone pairs on the boron?
0.
Okay. What's hybridization of the boron? sp2. Boron is group 3. It's only supposed to have 3 electrons. And so it has empty p orbital. Is it a cyclic conjugated system?
Yes.
Yes, if it, let's say yes to begin with. If it is, what is it, aromatic or anti? Be anti-aromatic. Be 4 pi electrons. Here's the final question. Is Parole aromatic? No, Parole is not aromatic. Is it anti?
Maybe.
Maybe. It depends on if it's avoiding it somehow. It's similar to the carbocation. Why would it become sp3? There's really, maybe some reason it does. I don't know. It's definitely not aromatic. Everybody understand why it's not aromatic? It doesn't have 6 pi electrons. Or 2 pi electrons. Or 10. That's what?
What would we consider it in this class, anti or non?
If we assume it's planar, then it's anti-aromatic. Question is that I don't know is it really planar? Or maybe for some reason it's non-planar and it's just non-aromatic. But it's definitely not aromatic.
Wouldn't it be a little difficult for it, I mean, with all of those being internal planar, would it be even difficult for it not to be planar?
Right. I think it is difficult. I think it's probably anti-aromatic. Okay, let's go back and do an MO diagram of one of these guys over here. Of the 4 ions, which one do you want to do an MO diagram of? Anybody? Middle bottom? This guy here? Okay, we said it's a cyclic conjugated system. How many p orbitals are we dealing with? 7 p orbitals. How many pi electrons in the system?
6.
7 p orbitals. Okay, how many MOs are we going to get?
7.
7 MOs. Okay. I'm going to draw the energy diagram. There's always going to be one at the bottom. That's where all 7 interact, plus, 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 all the way around. Okay? And as I said, as you go up, there's going to be 2, 2, 2 until you run out. There may be one at the top, or there may be none at the top. So, there's 1. We're going to do 2, 2, 2. There's 3. There's 5. There's 7. And guess what? There's not one at the top. Now this is energy. Where's the midline at? The midline is going to come right through here. Now there's 3 below and 4 at the top.
That's symmetric.
Now in terms of numbers of MOs, you cannot have an equal number on top and bottom. If we had drawn it right through here, there'd been 3 below and 2 on the top. How do you know how to draw the midline? On the Key to Drawing Molecular Orbital Diagrams, it talks about the frost mnemonic. These can be your energy distribution diagram for your MOs actually looks a lot like the molecule. If you draw benzene, let me do it without the pi bonds. Let's just draw the 6-membered ring. If you draw the point down and make that boom, 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 there's your MOs. Because if we do this without the ring, it's boom, 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 boom. Now my bonds here are a little long, okay? And the midline runs right through your molecule. Okay? 3 below, 3 above. Now the 4-membered ring, you've got to draw the point down. You draw the 4-membered ring like this. You get 1, 2, 3, 4. The midline comes right through the middle of the molecule. And you see you had 1 below, 1 above, and 2 on the midline. And the 2 on the midline we called what? Non-bonding. Okay? Now if you take your 7-member ring, draw the point down, let's just say it's turned a little bit. You go 1 at the bottom, then 2, 2, 2, 2, 2, 2. 1, 2, 2, 2. 1, 2, 2, 2. The midline goes right through your molecule. Now right through the molecule is actually sort of here. If I draw it more like, okay? The 3 below and 4 above. That's probably discussed in the book. It's shown at the bottom down there. Okay? It's called the frost mnemonic. In the end, you don't really need that too much if you just remember 1, 2, 2, 2. It's just getting the midline. Okay. Now if we drew these, we would sort of kind of be able to draw these because we have, this has 0 nodes. How many nodes does this level have? 1 node, 2 node, 3 node. So that would kind of help us. How many pi electrons in the system? 6. There you go. And so for the cation there, 6 pi electrons, what do we see? All electrons paired. You can't tell it's a cation by looking at this. I mean, you just know it's a cation because it's missing 1 electron. So that's an example of an odd number. All right. I kind of did this quick, abbreviated. There's other things we could do here. Homo, lumo. These are anti-bonding MOs, you know. These are bonding MOs. let me, that finishes up aromatics, I believe. Any last questions about aromatics? I know there's this one MO problem in the workbook. There's a sheet of structures for classifying as aromatic, anti-aromatic, etc. Yeah, let's look at one miscellaneous thing. This is an NMR application. We've seen this before. Anisotropic effect. Why? This is supposed to be benzene pi system. Why is the hydrogen of benzene more deshielded than an alkene? A pi system creates its own local magnetic field. It has this directional current. Out here where the H is, the current is reinforcing the external field. So is that a shielding or deshielding? Deshielding. I mean, if you're at the beach and something is reinforcing the amount of sun, do you call that shielding? No. No, by default you call it deshielding. This is the deshielding effect out here. Look down here at this guy. This is very interesting. This big guy looks like a cyclic conjugated pi system. You have to count the p orbitals and the pi electrons. But there's two types of H's here on this hydrocarbon. The H's that end up in the middle and those on the periphery. Those in the middle give a signal at -3 ppm in the NMR, a negative value. Because it's minus, we would say it's strong shielding. What leads to this strong shielding? What about those on the outside? 9.3, which is actually more deshielding than regular benzene. Okay? Well, those on the outside are just kind of like this. And because it's such a large pi system, you just get a larger effect. Because it's a larger pi system. Those that are in the middle is analogous to this with the H sitting here in the middle. Now, pretend this is sort of hollowed out and you got an H in there. Well, how is the local current in the middle? You see this? In the middle, it's actually what? It's actually shielding. See, these H's are sitting in the middle there and experiencing a strong shielding effect. That's actually evidence for aromaticity. Because if this thing was not aromatic, all of these H's would be where in the NMR? It would all be about 5 to 6, which is your alkene region. It'd just be an alkene. See, this is really a very nicely delocalized aromatic system. We can see that from the NMR data. But isn't that that's an odd position, yeah? -3? That's a result of the aromaticity in the ring current, where those H's sit. Nomenclature, I want to do a little bit another time. I actually may do that by video. Let's just set the stage for EAS, but then I do want to look at this carbon NMR. Okay, we have a purple. Please look at the warm-up type of questions. And then our working handout will be this. And our first mechanism we will look at is called electrophilic aromatic substitution, EAS. It's the most prominent major mechanism for aromatics. EAS. Please be doing this, doing some reading. Sounds like some of you have already been doing some reading. Nitration is an example of an EAS. This weekend lab will be reducing the nitro to the amino. You have a choice of either using, I think, zinc or tin, maybe. So your choice. We'll see if there's any questions about that lab on Wednesday. Please be doing some looking at that. Let's look at carbon NMR. Last here. Also need to return labs. I was only able to get Thursday's lab completed. The other lab, Friday lab, I'll have to return on Wednesday. I'm running a bit behind, especially with the test last week. I'll pass that out as we exit for Thursday lab. Okay, in the last couple of minutes, let's see. Sulfanilamide lab. I think we're going to have it due on Monday here in class. So a week from today, sulfanilamide lab will be due. Okay, we will cover EAS this week. Carbon NMR portion of the sulfanilamide lab here. We can actually do some calculations for the benzene carbons. Okay, we know it's in the carbon NMR, it's like 120, 150 range. You can actually do calculations. For example, here's a compound here. We expect 4 signals, A, B, C, and D, with it being symmetrical. Again, 120, 160, but where precisely? We can calculate these by this manner. We start with 128.5. That's where benzene is just benzene with no substituents. Then we say, okay, how does this change the value and how does that change the value? That's called a substituent shift effect. Well, guess what? On the back side is a list of what substituents do. Okay? You'll need to memorize this for the test. If you know me, you know that we never memorize any of this. You know, you go look it up when you need it. I mean, come on. What you do is, for example, A. How do you calculate A? You start with the base value. Then you add, okay, what is the effect of the aldehyde group? We also have to have a position. We haven't talked about positioning, but this is called ipso, is the substituent on the carbon we're talking about. What is the value for an aldehyde ipso? You look over here, you find aldehyde, usually it says CHO. C1, or also known as ipso, that's the carbon that the group is on. It adds 8.6 to the value. Ortho is the adjacent carbon, meta is the carbon after that, and then para. We'll see this on nomenclature, but some of you kind of already recognize that. So, aldehyde ipso is what? 8 point, is that a 6?
Yeah.
Okay. Now, we also have the effect of the methoxy. Now we're talking about A here. The methoxy is not ipso, it's not ortho, it's not meta, but it's what?
Para.
It's para to A. What is the effect of methoxy when it's para to a carbon? Where's methoxy? Where's the NO2? Right here. Well, that's a big effect, but we're not, where we want para?
The last one.
Negative 7.7. That's what it does. So in calculating A, you just list the values, add it up, and you get what? 129.4. Actually, not a big change. That's what we predict. Okay? Go through this. For example, C. We want to say, hey, what is the effect of methoxy ortho to C? That means it's adjacent to C. And then it's also got an aldehyde meta to C. Okay? And then you get those values, and then that ends up for what you predict. Here's the kicker, guys. There will be a good amount of error here. The more substituents you have on your ring, the more error you're going to get. Now you have either 3 or 4 substituents. If it's 4 substituents, it will be a good amount of error. But you can still use that. For example, you got one that's way downfield. If you end up with a peak at 180, which one looks like it's the closest to 180? Okay? It may not be 180, but you can still say, hey, it must be this one. Because that's the one that's closest to 180. Okay? See if you have any questions, ask on Wednesday. That's what you'll need to use for the carbonated bar part of the sulfur lab. Okay, guys, have a good week.
We're getting a lab back?
Lab back, yes. Please yell. Thursday lab, D-Raj. Nick, here. Sana. Kayla. Vamsi. Sarbani. Nancy. Stephanie.
Just close it.